NGC 244.
WASP 39B.
NGC 6826.
Names play an important role in physics.
In the end, everything, every mathematical equation, every symbol, everything that we do has to be put into language. And so language matters.
Up quark.
Down quark.
Strange quark.
Charm quark.
Bottom quark.
Top quark.
But while names have the ability to clarify thought, they can also muddy the waters.
The question that arises with these ideas, such phrases, is, are they correct ideas or are they misleading ideas?
TP53.
TNF.
EGFR.
ESR1.
IL6.
You've heard the buzzwords: the Big Bang, dark matter and dark energy, quantum particles with spin. But did you know that dark matter is not dark and may not be made of matter? Particles don't spin, and dark energy, well, you get the picture. The trouble with such terms is that the images they evoke may not correspond to reality, and could inadvertently send physicists down very specific research avenues and distract them from others.
Sometimes we run into problems where people who have a training in one way are not necessarily using the vocabulary in the same way as people who are trained differently. And I don't think that people are always aware of those differences.
I'm Zia Morali, and this is episode 3 of What's in a Name. In this podcast, I have gathered 5 stories about the importance of names and how much can be lost in translation when physicists try and name the unknown. We're starting at the very beginning, with possibly one of the best-known scientific terms in existence: the Big Bang. The name given to the moment some 14 billion years ago, when space and time exploded into being from an infinitely dense point, or singularity. Except, maybe that's not what the term Big Bang actually means. Depending on which scientists you are talking to, you could be talking about a different moment altogether. The fact is that the term we now all know means more than one thing, and it was not honed and created to help scientists and the public more broadly grasp the origin of the universe. It was actually, arguably, the product of a scientific rivalry, reportedly intended to ridicule, not inform. A somewhat crude metaphor to allow a scientific takedown on a radio show.
Initially, way back when, in the first universe models, there was a lot of resistance to the idea that the universe had a beginning.
This is George Ellis from the University of Cape Town in South Africa. He literally wrote the book on the Big Bang with the late Stephen Hawking over 50 years ago.
And Einstein, of course, the biggest error he made in his life was proposing a static universe model, because the universe is definitely not static. Then it became accepted that the universe was expanding, and it then became clear that classic universe models had a beginning. And the question is, what happened at that beginning, and was that beginning inevitable?
George Ellis and Stephen Hawking were not the first to suggest the concept that the universe grew from some tiny initial point in space, some primeval atom. That honour dates back to the 1930s with the work of Georges Lemaitre, a Belgian physicist who also happened to be a Catholic priest. And herein lies the beginning of a controversy surrounding the theory, which would ultimately lead to the coining of the term Big Bang. The idea that one point, or singularity, may also represent the origin of not only space, but time, gained favour with researchers like the Russian physicist George Gamow, but it brought with it some religious connotations which alarmed some scientists. One of those scientists, Fred Hoyle, allegedly hated the concept of a cosmic beginning as it appealed to the Pope. Hoyle took to Radio 4 in 1949 in an attempt to ridicule the concept of a cosmic origin. Searching for a metaphor to describe it, he referred to
the hypothesis that all the matter in the universe was created in one big bang at a particular time in the remote past.
He coined the phrase Big Bang as a kind of derogatory term, making fun of the people who were proposing that there was a Big Bang start to the universe. That phrase then stuck.
But it didn't stick initially. In fact, it would be a few decades before the term Hoyle coined would become adopted by the community at large, and in that time, the phrase Big Bang would shift in meaning, no longer simply referring to the moment when the universe exploded into being. In the 1980s, cosmologists posited that shortly after its birth, the very young universe went through a rapid period of inflation. And it is the period that followed inflation, after the initial beginning, that cosmologists called the hot Big Bang, when matter was literally at a very high temperature. However, the universe's origins before inflation, to this day, remain murky and shrouded in mystery.
And the idea that before the hot Big Bang epoch, there was this incredibly fast expansion, which was called inflation. Again, so the hot Big Bang nowadays is understood as being this later era following inflation.
And yet, if you ask your average Joe or Josephine on the street what the Big Bang is, they will almost certainly tell you it is the moment the universe came into existence. Even within the scientific community, things aren't clear-cut. Whilst for most researchers, the term Big Bang has evolved to refer to a hot, dense state in the universe's infancy, not its actual beginning, the two different usages of the term Big Bang are both in play. Particle cosmologists are more prone to referring to the mysterious Big Bang singularity, while astrophysicists often use the same language to refer to the later, hot Big Bang era in cosmic history, where they can collect observational data.
I do think cosmology, possibly more than other areas, you really have to be specific with people about what aspect of cosmology and where in the cosmological timeline you're talking about.
This is Chanda Prescott Weinstein, who is herself both a physicist and an astrophysicist at the University of New Hampshire in the United States. She notes that researchers often don't realise they may be speaking at cross purposes with their colleagues.
Actually, a few years ago, I got into it on social media with someone. This person was making the claim that Big Bang never refers to this very beginning, air quote, moment, and only ever refers to this era in cosmic history known as the hot Big Bang. And I was like, that's simply not true. The Big Bang gets used both ways.
The fact is, this one term means different things to different scientists and different disciplines, and that can sow confusion.
So I do think that sometimes we run into problems where people who have a training in one way are not necessarily using the vocabulary in the same way as people who are trained differently. And I don't think that people are always aware of those differences.
And yet, regardless of whether the Big Bang denotes an expansion of space and time or an explosion that created space and time, the image that it conjures, that there was a bang and it was big, is reasonably accurate. So in that sense, Fred Hoyle's mocking term has been, perhaps to his chagrin, extremely successful. But the names chosen to describe physical phenomena don't always conjure a useful picture. In fact, they can make us inadvertently visualize the wrong thing. And that brings us to our second story, where the names chosen to describe the quantum world of subatomic particles can sometimes, accidentally, put the wrong spin on things.
Physicists and mathematicians, unlike a lot of other sciences, literally have to kind of make stuff up sometimes.
This is Ian Durham, a quantum physicist from St. Anselm College in New Hampshire in the United States.
Or they grab these words from other places, and they don't necessarily have any relation to physics or mathematics because they need a way to describe something extremely complex. In the end, everything, every mathematical equation, every symbol, everything that we do has to be put into language. And so language matters.
One of the most famous borrowed words is quark, the name given by American physicist Murray Gell-Mann to the subatomic particles within protons and neutrons, which was borrowed from a line in James Joyce's Finnegan's Wake.
3 quarks for Muster Mark. Sure, he hasn't got much of a bark. And sure, any he has, it's all beside the mark.
Gell-Mann used this name because there are 3 quarks in the poem, and quarks cluster in groups of 3 inside protons and neutrons. Cute. But this case is fairly innocuous. After all, quark isn't a common word whose everyday meaning might have caused a mix-up with its scientific definition. But sometimes, the choice of name can create confusion. In his 1928 book, The Nature of the Physical World, British physicist Sir Arthur Eddington cautioned against taking descriptions of physical processes too literally. We should understand, he said, that really we mean
something unknown is doing we don't know what.
A case in point is the term spin, the name given to a weird internal quantum property of tiny particles. We often say, for instance, that an electron can be visualized as a tiny basketball twirling on someone's finger. But due to so-called quantum effects, this particle can only spin either clockwise or counterclockwise. But in reality, electrons do not spin at all. The name is entirely inaccurate. And the story behind the discovery and naming of spin has some twists and turns of its own. In fact, the name spin was responsible for the concept not coming to light earlier. Today we credit the discovery of spin in 1925 to a pair of young Dutch physicists, George Erlenbeck and Samuel Goudschmidt, who were then still students. Erlenbeck and Goudschmidt were investigating the wavelengths of light absorbed and emitted by hydrogen atoms, which show up as a unique series of lines in the atom's spectra. The pair were trying to interpret an odd additional feature of the spectra that appeared when the atoms were placed in a magnetic field. At the time, physicists had begun to realise that atoms appeared to be spinning because they displayed magnetic effects that could only be explained if they were rotating, which could in turn affect their spectra. So it was natural enough for Erlenbeck and Goudschmidt to propose that their new line may be explained by something similar, specifically that the constituent electrons in the hydrogen atoms, and by extension all atoms, might literally be spinning too. And the students submitted a paper suggesting as much to a journal. Their supervisor at the time, Paul Ehrenfest, was taken with the idea, describing it as, quote, very witty. And yet, they hit a snag when they mentioned the finding to Nobel laureate Heinrich Lorentz. Here's Ian again.
Lorentz pointed out that this idea actually is completely incompatible with classical electrodynamics. And he basically said that the electron, if it was spinning like the Earth, its surface would have to be spinning faster than the speed of light.
Faster than light travel is an impossibility according to the laws of physics. So a literal interpretation of spin, in which an electron rotated faster than the speed of light, was seemingly ludicrous. So much so that Lorentz and other famed physicists of the era ridiculed anyone who discussed it, including another German physicist, Ralph Koenig. In fact, they had shamed Koenig into not publishing the same idea when he had come up with it earlier. Goudschmidt and Erlenbeck were so embarrassed by their mockery that they asked their supervisor if they could retract their paper. Luckily for them, their supervisor advised against retraction, with the not too comforting words, "You were both young enough to be able to afford a stupidity."
And then eventually Uhlenbeck and Goudschmidt, we remember them now in hindsight as this being this great discovery.
Indeed, spin is now considered a quintessential quantum effect. Physicists have since got round the worry that electrons would need to be spinning at faster than light speed by saying that electrons are point particles that have no size, a radius of 0. This has led to a rather extreme mismatch between the words used to describe the phenomenon and physicists' actual understanding of what's happening.
We have now evolved to the point where we say, well, when we talk about an electron that's spinning, there's nothing that's spinning because there's nothing there. It's a point particle. It doesn't have size.
Little wonder, then, that in his book, Sir Arthur Eddington whimsically referenced Lewis Carroll's poem Jabberwocky when he recommended that, when discussing subatomic particles, it might be better to say,
"The slithy toves did gyre and gimble in the wave."
Using such nonsense words would avoid generating any misleading visualizations in people's minds. The subatomic world is, after all, governed by the weird rules of quantum theory that notoriously defy common sense logic. Which brings us to story 3. What of the word quantum itself? Here's Ian again.
I will say quantum is worth talking about simply because it is one of the most abused words in the English language. Marketing people love the term. I think people think, oh, if I stick the word quantum in it, it sounds cool. But just because your company that makes inkjet printers has a quantum inkjet printer doesn't mean it's doing anything quantum.
In the early 20th century, German physicist Max Planck used the Latin word quanta to explain that the light and heat energy radiated from certain hot objects, from stars to tungsten light bulbs, doesn't come out as a continuous wave, but in bite-sized chunks.
The original meaning was essentially to quantify something. It's got the same root as the word quantity.
Planck's discovery of energy quanta formed the bedrock of quantum theory, which historically described the rules at play when you zoom down to small scales and examine the microscopic realm. And since technically a quanta describes a minuscule amount of energy, the smallest chunk of energy possible, in fact, this led the word quantum to become strongly associated with a second meaning, with all things tiny.
So I think that term has, for a long time, limited people.
Ian argues this latter connection may have inadvertently held up physicists, preventing them from fully understanding quantum theory.
The thing is that the theory, as it's been fleshed out over the years, says absolutely nothing about the size of the objects to which it applies. There's nothing in the theory that says it has to apply to only small things. But I'd say for 80 or 90 years, people were stuck in this idea that quantum meant small.
This historic association with the very small makes a lot of sense, because quantum theory tends to be applied to the subatomic world, and we don't see quantum effects in everyday life. Nonetheless, Ian contends, this choice of language may have discouraged physicists for decades from considering that quantum theory could be applied to larger things. But that has been gradually changing over the last decade, even if the shift has been somewhat contentious.
People have started considering whether quantum mechanics plays a role in consciousness. I will say that this work is controversial, but there are new theories out about consciousness itself being a quantum field.
Quantum and spin, then, are examples of words that initially seemed to be good choices based on the features of the phenomena that physicists were attempting to describe. But the words were inadvertently loaded with imagery that might have dissuaded physicists from pursuing productive new lines of thought. That problem can be amplified when you're trying to name something, or some things, completely unknown, the subject of our fourth story.
I think there's the interesting philosophical question, which is, how do we name something when we don't understand what it is? So we need a placeholder in order to have conversations about it.
This is Chandra Prescott Weinstein, whom we heard from earlier. Part of Chanda's research involves trying to uncover the identity of dark matter, the unseen substance that many physicists now think makes up about 85% of the matter in the universe. In the 1930s, Swiss astronomer Fritz Zwicky realized that the motion of galaxies could not be explained by the influence of gravity acting on the visible matter we could see through telescopes alone, suggesting something else is there. He coined the term dark matter for this inferred hidden and unknown substance lurking in the universe that doesn't emit radiation and so cannot be seen in a conventional way. But for the best part of a century since then, astronomers have been wringing their hands trying to detect dark matter or identify what it might be made of. Chanda devotes much of her research to understanding one potential particle that was proposed to clean up this dark matter problem.
I work on the axion. It's a hypothetical particle that we've never observed, but I spend a lot of time thinking about what it will do if it's out there. And the name for that particle, the axion, Frank Wilczek came up with axion because at the time that he was thinking about it, there was a popular laundry detergent called Axion. And that's actually not the end of it, because you can say, well, where did the name for the laundry detergent come from? And that actually comes from Greek liturgy, from the Axion Estine, which is a prayer to Mother Mary. We have this hypothetical dark matter term that's actually got this deeply religious name, but arrived to us via laundry detergent.
So physicists clearly can be knowingly playful when coming up with names, without too many qualms about the roots of those words. That's usually harmless. But is dark matter itself a good name? Some physicists have argued that one of the reasons researchers have struggled for decades to identify the substance that makes up dark matter is that there is no actual hidden matter out there to be discovered. What's more, they say, by choosing the term matter, Zwicky accidentally set future generations of researchers on a wild goose chase, searching for something that may not actually exist. An alternative suggestion, a minority view in physics for a few decades, is that in fact there is no dark matter. Instead, our understanding of how gravity works on cosmic scales needs to be modified. Put a pin in that thought, because we'll come back to it in a bit, but not until we have introduced you to another potentially misleadingly named astrophysical phenomenon. In the 1990s, astronomers discovered that the universe is not only expanding, but that the expansion is weirdly picking up speed. They needed some mechanism to explain this, so American cosmologist Michael Turner came up with the label dark energy, somewhat in jest. In fact, he considered it as a placeholder for this unknown source of the universe's accelerating growth.
I've heard Michael say that they were just well, it's like dark matter, but it's not. That was the flippant thing, is that it was just a name for a phenomenon that seems to be invisible, but also is highly impactful. I think this is also a great example of physicists are sometimes having fun, and that fun isn't necessarily legible to the people who weren't in the room or to the people who don't have our training.
Some of the same researchers who argued that the name dark matter may have misguided physicists into looking preferentially for matter that doesn't exist also argue that the term dark energy automatically sets astronomers on the hunt for a new or overlooked form of energy. The conventional view for some decades now has indeed been to search for these literal missing entities, and it should be said that in recent years, observational evidence has seemed to back this more mainstream approach. However, there is a small but vocal minority of physicists who are investigating the alternative idea, mentioned earlier, that both astrophysical mysteries can be solved just by rethinking gravity. This rival view has invited far less interest over the decades, and that raises the question: why? Some argue that the answer is that names have power, and perhaps sociologically, concepts just catch on better if they have a cool name attached, especially if that name makes an amorphous concept easier to visualize. Here's cosmologist George Ellis, whom we heard from earlier.
I think there is a sociological factor. I think people start thinking in a particular way. It's difficult to get them to think otherwise. These words, these phrases, they capture an essential idea, which is a very important idea, and they can then generate a whole research program. The question that arises with these ideas, such phrases, is, are they correct ideas or are they misleading ideas? Are there alternatives which could be pursued? And so you follow this idea and then that closes off your mind to following other ideas. And that is one of the things which occurs in all of these cases.
In terms of dark matter, to avoid misleading assumptions, some researchers have shifted to using the subtly alternative phrasing, missing matter. Calling it the missing matter problem also solves another issue. Namely, it moves us away from the word dark, which can have entirely separate, unwanted connotations. Chandra is one of fewer than 100 black American women to have earned a PhD in physics, and has written about the misuse of language in physics based in part on her own experiences. She notes that the term dark matter is not really an accurate description of the physics, and has even been used problematically in some wider academic circles as an analogy for people of colour, whose experiences and opinions have been hidden from view.
I was kind of horrified when I realized that people were making these comparisons between people of color and dark matter, because it was really predicated on some level on a misunderstanding of what dark matter means when it's in circulation in the physics community, which is not about a color, but is specifically about a phenomenon that's transparent and distinctly different from visible matter. On some level, the movement for Black lives has again brought to the fore that Black people are visible matter. Black people are luminous matter. And also, I think this is a great example of different dialects, that dark has a particular meaning to folks in Black and brown communities that it doesn't necessarily have for people who are white. There's this grand sort of Western tradition of dark as foreboding and evil and scary, and that is entangled with these questions of racism and colorism.
Language choices in physics, then, can have the consequence of making physicists of different backgrounds feel excluded or uncomfortable. Chanda notes that with the analogy between dark matter and people of colour, this outcome was unintentional, with academics in the humanities seizing on the term dark matter for its poetic power, without fully thinking through the implications. But Chanda argues that the problem isn't contained within the realms of research. In fact, she suggests that it can have further-reaching implications, and that is because science and scientists tend to carry a certain authority, and that authority leads to these scientific terms being co-opted, spreading beyond the halls of academia. We touched on it earlier with the incorrect use of the word quantum in marketing and ad campaigns. This adds an extra layer to the way in which the choice of words in physics can be inadvertently misleading. The effects can be compounded when they escape beyond the technical jargon-filled arenas where they were originally defined.
It's interesting how scientific vocabulary makes its way into the wider public awareness because of not just the mystery that's attached to it, but the power that's attached to scientific expertise and scientific knowledge and cosmic mysteries. Not just, the awe-inspiring part, but also the way that we as a general public have been told that the people who think about these kinds of questions are our community geniuses. Like scientists are geniuses, theoretical physicists are geniuses.
And perhaps here, physicists have to accept a little bit of the blame for encouraging this grandiose image, and maybe even exploiting it. In our final story, we'll turn to a topic the public has been hearing about for over half a century: the ultimate physics quest for a theory of everything, that would unite our understanding of all the forces of reality under one umbrella. The term theory of everything has not only stimulated physics research programs, but spawned headlines, bestsellers, and even a couple of movies. Also sometimes going by the less illustrious acronym, the TOE, it's a term that inspires passion, of a kind, in Ian, George, and Chanda.
TOE, the toe. What does that even mean? Where in the fundamental equations of everything are the equations that govern consciousness? Does your theory of everything explain bank overdrafts? I'll say it's a term, you can edit this out if you wish. It's a term used to sell books.
What is meant by a theory of everything is a theory of everything that is interesting to a small group of particle physicists. It is not in any remote sense the theory of everything. It has nothing to say about chemistry, about biology, about sociology, and to call it a theory of everything is simply a highly misleading kind of name, and I think the public must be really aware of that.
I absolutely believed as a teenager that if we could solve quantum gravity, that it was a theory of everything that would help us understand how to live better. And then I grew out of it. That was the public line, was that science is salvation, right? And I really thought if we solve quantum gravity, then that will give us the equations that describe everything. And then we will know how to calculate what is the fair economy. I think there's a kind of dangerous hubris associated with it.
So maybe physicists are both the victims and perpetrators of misleading language choices, sometimes made on little more than a whim, but with full knowledge that catchy slogans like the hunt for a theory of everything will attract both their colleagues and the public. The consequences of ambiguous word choices can range from generating short spats between scientists on social media, as with the term Big Bang, to steering the course of physics research programs, for good or bad, for years, or even for the better part of a century, as with the words quantum, spin, dark matter, and dark energy. They say a picture is worth 1,000 words, but in the case of physics names, the images accidentally conjured up by a misnomer might cost physicists years, if the true description of reality is lost in translation. Episode 3 of What's in a Name was written and produced by me, Zia Morali, with production help from Benjamin Thompson and Noah Baker, with thanks to Nick Petrich-Howe, Shamini Bundell, Anne-Marie Conlon, and Noah Baker for additional voice work. For a full list of references and music used, head over to the show notes on the Nature Podcast website.